is a critical situation in any aircraft. In a multi-engine airplane, you have more options to deal with the problem than in a single engine. This section looks at some of the considerations associated with an engine failure in a light twin. The first step is a thorough understanding of engine-out aerodynamics. We'll begin with the most serious engine-out situation, loss of the critical engine in a conventional twin. You'll remember that in a twin-engine airplane with both propellers rotating clockwise, the loss of the left, or the critical engine, causes the most significant directional control problems. Changes in lift, thrust, and drag are the forces that produce these problems. For example, the lack of induced airflow over the left wing produces an imbalance in lift. This asymmetrical lift causes a rolling tendency toward the inoperative engine. The torque of the good engine's propeller adds to this rolling tendency. The asymmetrical effects of thrust, aggravated by P factor, produce a yaw toward the inoperative engine. This yaw also causes a further loss of lift since the flight path is no longer parallel to the longitudinal axis. And part of the airflow over the left wing is blanked out by the fuselage. As you deflect the control surfaces to overcome the roll and yaw, total drag on the airplane increases. Aileron drag acts asymmetrically because the down aileron produces more induced drag than the up aileron. The rudder deflection needed to overcome yaw adds to the total drag. Also, the windmilling propeller produces a great deal of asymmetric drag. Although an engine failure cuts available horsepower in half, the combined effects of asymmetrical lift, thrust, and drag cause as much as an 80% loss of performance. Although these same factors are present in aircraft with counter-rotating propellers, the prop rotation minimizes some of the adverse effects. For example, if the left engine fails, the torque of the operating propeller now opposes the asymmetrical lift generated by induced airflow and reduces the rolling tendency. Asymmetrical thrust still causes a yaw toward the failed engine, but the effect of P factor is less. This is because the descending propeller blade is always the one closest to the longitudinal axis. Regardless of the type of airplane, as you slow it down, you reach a point where the rudder can no longer counteract the yawing tendency. At this point, called VMC, the airplane will become uncontrollable unless you take immediate action. Each multi-engine airplane has a VMC that's established under a specific set of conditions. This normally includes the aircraft loaded to maximum takeoff weight, the center of gravity in the most unfavorable position, the critical engine inoperative, the propeller windmilling, the operating engine producing takeoff power, the gear retracted, the flaps in the takeoff position, and up to 5 degrees of bank established toward the good engine. VMC relates only to directional control and has nothing to do with an airplane's ability to climb or even maintain altitude. It is shown as a red line on the airspeed indicator of multi-engine airplanes. It's important to realize that at any given time, an airplane's actual VMC may vary due to changes in weight and balance, density, altitude, power settings, and aircraft configuration. It's a common misconception that when an engine fails, a twin is flown wings level with the ball centered. Let's look at why this is not a good practice. The yaw of an engine failure causes the ball to move toward the operating engine. The amount of rudder pressure required to center the ball actually produces a side slip toward the inoperative engine. Flight tests have shown that this configuration may increase VMC as much as 20 knots and may reduce climb performance by 300 feet per minute in some airplanes. A much better procedure is to bank the airplane approximately 3 to 5 degrees toward the good engine and let the ball deflect about 1 ball width toward the operating engine. This configuration produces a zero side slip and requires less rudder pressure to maintain a streamlined flight path. As you can see, engine-out aerodynamics are a challenge, but the knowledge is vital to your capability as a multi-engine pilot. Let's turn our attention now to some engine-out performance definitions. An airspeed you will probably use in your training is VSSE, or the intentional one-engine inoperative speed. This is a minimum airspeed established by manufacturers for intentionally rendering one engine inoperative during training. When you practice single-engine airwork, you should never feather a propeller below 3,000 feet AGL. As we mentioned before, VXSE is the best single-engine angle of climb airspeed. This is an important speed during a maximum performance takeoff over an obstacle. If an engine fails after you're airborne, you use this airspeed to clear the obstacle. The best single-engine rate of climb speed, VYSE, sometimes called blue line airspeed, has several applications to multi-engine flight. It gives you the best rate of climb, or the slowest rate of descent if you can't maintain altitude. Another application of VYSE is in connection with the single-engine service ceiling. This ceiling is the maximum density altitude at which VYSE will give you a 50 foot per minute rate of climb with one engine inoperative. The single-engine absolute ceiling is the maximum density altitude an airplane can reach and maintain on one engine. Now that we've discussed the theory of engine-out flight, let's look at some practical applications. The first engine-out operation we'll cover concerns the procedures to follow in case of an engine failure. If you ever have to shut down an engine, it's imperative that you use the checklist in the pilot's operating handbook to make sure that all tasks are done properly. The manufacturer may recommend that you commit some items to memory, but after completing all actions, you should refer back to the checklist to ensure that those items were accomplished. In the event of an engine failure, there are several general steps to follow. Your first step is to apply full power. Then, reduce drag, identify which engine has failed, verify that you have correctly identified the failed engine, and finally, shut down the failed engine and feather the propeller. Let's take a closer look at each of these steps. Once you realize an engine has failed and you have the airplane under control, apply maximum power by moving the mixtures, propeller controls, and throttles forward. To reduce drag, you will usually raise the landing gear and retract the flaps. The actual sequence depends on the situation and your configuration. Always follow the manufacturer's recommendations. There are several clues which help you identify a failed engine. Your initial indication will be a roll and yaw toward the inoperative engine. The control inputs you'll make to counter that motion will include applying aileron and rudder toward the good engine. Rudder pressure is a primary indicator of which engine has failed. The foot corresponding to the failed engine will not be applying rudder pressure. In other words, idle foot, idle engine. In this case, the left foot is idle, so the left engine has failed. The engine instruments may or may not help you determine which engine has failed. For example, if the engine has quit from fuel starvation, the fuel flow gauge for that engine will be at 0. However, the manifold pressure and RPM for the failed engine may be close to normal because the relative wind still drives the constant speed propeller at the set RPM, which in turn drives the engine. Once you've identified the failed engine, you can verify it by retarding the throttle of the suspected engine. If you selected the correct engine, there will be no change in the rudder pressure required to counteract the yaw. If you select the wrong engine, the yawing tendency will decrease. Immediately advance the throttle to regain maximum power. Once you have verified the inoperative engine, shut it down by moving the propeller control to the feather position and pulling the mixture to idle cutoff. Use the checklist in the pilot's operating handbook to accomplish all the actions for securing the failed engine. When you've stabilized the airplane in single-engine flight, trim off the control pressures and monitor the operating engine for any signs of overheating or other malfunctions. Let's continue our discussion with a look at engine-out maneuvers. We'll begin with takeoff considerations. An engine failure during departure requires a rapid assessment of the situation and immediate action. Evaluating the options before takeoff makes your decisions much easier. For example, always compare the density altitude with your airplane's single-engine service ceiling. If you fly when the density altitude exceeds this ceiling, you may have no option but an off-airport landing should an engine fail. However, you can improve the situation by waiting for better conditions or making the flight with less fuel, passengers, or baggage. You should also make sure that the accelerate stop distance for the existing conditions is not longer than the available runway. Just before takeoff, review the procedures and airspeeds to follow in case of engine failure. This includes a plan of action to avoid obstacles if your climb performance is suddenly reduced. Always know what your airspeed, altitude, and configuration must be for you to continue the takeoff after an engine failure. If an engine failure occurs on the takeoff roll below VMC, the airplane will immediately turn toward the failed engine. Your only choice is to close both throttles to maintain directional control and abort the takeoff. If an engine fails just after liftoff, you must make an immediate decision whether or not to continue. If you have not begun to retract the gear and there is enough runway remaining, close the throttles and land. If you decide to continue the takeoff, you must maintain positive control of the airplane and accelerate to VYSE. If there are obstacles to clear, accelerate to VXSE. Either of these may require a momentary descent. Make sure the engine controls are set for maximum power, and once you have a positive rate of climb, reduce drag by retracting the gear and flaps according to the manufacturer's recommendations. Make sure you've identified and verified the failed engine, and shut it down. Remember that this procedure is only a typical example. You must perform the exact sequence of steps given in the pilot's operating handbook. During the climb, maintain VYSE and keep 5 degrees of bank toward the operating engine. Even if you can't establish a climb, you should maintain VYSE since that will give you the slowest rate of descent and allow you the most time to prepare for an emergency landing. While an engine failure during the en route phase of flight may not be as serious as at takeoff, you should still apply full power to conserve altitude while you take care of the situation. Once you've identified and verified the inoperative engine, try to determine the reason for the failure and restart the engine if practical. If you can't restart the engine, use the checklist in your pilot's operating handbook to shut it down and feather the propeller. Once you've done all the checklist actions, you should head to the nearest suitable airport and land. Remember that the airplane will fly best if you maintain 5 degrees of bank toward the good engine and use trim to relieve the control pressures. You should maintain altitude if at all possible. However, if the engine fails while you're cruising above the single-engine service ceiling, you'll have to descend at VYSE to that ceiling. This is particularly significant if you're over high terrain. Obviously, your pre-flight planning should include reviewing areas of lower terrain and the locations of alternate airports. Remember, descending at VYSE gives you the slowest rate of descent and conserves altitude for the longest time. For a long flight, use the fuel cross-feed system on the aircraft to maintain fuel balance. You especially want to avoid having a heavier fuel load on the same wing as the failed engine. As you get close to the airport, plan for the approach and landing well in advance and fly a stabilized descent to the traffic pattern. Maintain the airspeed at or above VYSE throughout the pattern until the landing is assured. You may want to fly a larger pattern to allow for shallower turns and better visibility. Do not lower the landing gear until the landing is assured. Delay lowering any flaps until the gear is down and you are absolutely certain of making the runway. Remember that as you decrease power on the good engine during the flare, the yawing tendency you've been correcting for will decrease. So be positive with your control inputs to keep the airplane straight down the runway on the rollout. One of the most important reasons for planning your engine-out approach thoroughly is to avoid the need to make a rejected landing. Under certain conditions of airplane weight and density altitude, this maneuver may not be possible. Part of your approach planning should include a go, no-go altitude for a rejected landing based on airplane performance, obstacles, and terrain. If a go-around becomes necessary, make your decision as early as possible. Carefully add full power on the operating engine and smoothly raise the nose to establish a shallow climb. Reduce drag by raising the flaps and landing gear and accelerate to VYSE. Once again, follow the specific procedures outlined in your pilot's operating handbook. The last maneuver we'll discuss is officially known as engine inoperative, loss of directional control demonstration. It is one of the most important maneuvers you will practice in your multi-engine training. This maneuver shows you how to maintain directional control with an engine inoperative and the procedures to follow when directional control cannot be maintained. As with other multi-engine maneuvers, 3,000 feet AGL is the minimum altitude for performing and recovering from this demonstration. The proper configuration for the demonstration is with the propellers set to high RPM, the landing gear retracted, both the wing flaps and cowl flaps at the takeoff setting, and the trim set for takeoff. Establish the airspeed at VYSE and reduce the power on the critical engine as recommended by the manufacturer. Smoothly increase the pitch attitude to bleed off airspeed as you add climb power to the operating engine. Establish a 5-degree bank toward the operating engine and maintain the heading with rudder pressure. As the airspeed decreases, you will eventually reach a point where full rudder is not effective enough to maintain the heading. As soon as this happens, recover by simultaneously reducing power on the operating engine and decreasing the angle of attack. As you regain directional control, complete the recovery by slowly increasing power on the operating engine and establishing the airspeed at VYSE. In some cases, a high-density altitude may keep you from performing this maneuver. The reason for this is that the calibrated stall speed of an airplane remains the same regardless of altitude. The VMC published in the pilot's operating handbook is established at sea level. But as altitude increases, the actual VMC decreases because the operating engine is developing less power. Above a certain density altitude, the actual VMC is less than the stall speed, and you will start to get indications of a stall before you lose directional control. In this situation, the demonstration should not be attempted. Having one engine at idle and the other at full power as you approach a stall is extremely hazardous. This is one of the reasons you should always have a qualified instructor on board when practicing this maneuver. Up to now, we've only talked about visual maneuvers. In the next section, we'll cover instrument flight in a multi-engine airplane.